Hello, here we are for free fall questions in problem set 1 for honors physics. And right now we're taking a look at question 2. How would you estimate the maximum height that you could throw a ball vertically upward, assuming that you can throw it at 20 meters per second? First thing is I want to say that we're just trying to do an estimate, a really rough estimate. And it's one of these conceptual questions, not really meant to be so much of a calculation sort of thing. So we're going to like round things off and do calculations that we could do in our head maybe. At least that's the plan. So what I'm going to do is I'm going to draw a sketch. Sketches help me solve problems and help me figure out problems. So I'm going to have this ball and I'm going to throw it upward at 20 meters per second. As it goes up, it's going to get slower and slower until it gets to the top, and then it would start to fall back down, getting faster and faster, right? And so what I'm concerned with, I'm just concerned with it going from here up to the top. And what I'm going to call that topmost point in this motion, I'm going to call it the peak. Okay, and I'm imagining going straight up and straight down. I just didn't want to draw on top of myself, so I drew off to the side. But we're just looking at going up, straight up to the peak. So when I think about doing motion calculations, kinematics calculations, with constant accelerations like this, I usually think about the 5 variables that are popping up in our formulas. And I kind of see like which variables I have to work with here. Now they told me that I'm going, first of all, once it leaves my hand, the only force acting on that ball is gravity. And that means the acceleration will be the acceleration caused by gravity. That'll be that negative g, or if you like, negative 9.8 meters per second squared. Okay. The starting speed, we know that we threw it upward at 20 meters per second. And again, that naught means the original or starting speed. Now, at the end, I'm looking at, I want to know how high I can get this to go. I want to know the displacement up to the top there, right? And so this is what I'm trying to find. I'll put a little question mark there. And you say, okay, well, that's great. I got 1, 2, 3 variables. The thing is, all the formulas that we have, V is AT plus V naught. V squared is V naught squared plus 2A delta X. Delta X equals V naught T plus 1/2 AT squared. They all have, each one has 4 of these 5 variables in it. And so if I got 4 unknowns, I need to have 3 knowns to solve for a 4th unknown. You know what I mean? And so right now I only have 2. So I need another value. Well, there's another value that we know. And it comes from recognizing that when you throw something upward and it gets to the peak, and then it's going to come back down, there's something special you know about the peak. So if I had a graph, because I have a hard time explaining things without graphs, if I had a graph, and this was my velocity, and this was time, then the graph for this, we know we have a constant acceleration. And you remember, acceleration on a velocity time graph, acceleration is the slope of the velocity time graph. We have a constant acceleration, negative 9.8, means we have a constant slope, right? It's a straight line here on that graph, the slope of negative 9.8. Now, because we're just estimating, I'm going to round these things off, all right? So let's just kind of get estimated values. Let's just call this negative 9.8. Can we just say that's approximately equal to negative 10? So then if I got the slope of that's approximately equal to negative 10. So one thing that I know is, look, when I'm going upward, the sign on the velocity is positive, right? And then when I come back down, the velocity is going to be negative. You say, look, to go from positive velocities to negative velocities, don't you always have to pass through 0? That would be when I'm at the peak. So we know that when you're at the peak, if you're throwing something straight up, straight down, at the peak, that vertical speed is 0. And so if I'm trying to find the height change from here to the peak, I can make the final velocity here, that's the V without a subscript, that ending velocity is going to be 0. Now I have 1, 2, 3 variables I could solve for the 4th. I would want the formula that didn't have T in it, that would be the second one, would be the handy formula to use if I was going to do the calculation. Can we do this really quickly in our heads? You say, sure. I could go ahead and I could say, look, a 0 for the final velocity, that term drops out. Initial velocity is 20. 20 squared is 400. We're going to round this a to -10. So looking at this here, v squared is v naught squared plus 2a delta x. Rounding this off, this is going to be 0, 20 squared plus 2 times -10 times displacement. You say, oh my gosh, look what's going to happen. Move this over to be 20 delta x equals 20 squared. Look at that. 20 times delta x is 20 times 20. Oh, look, delta x is about 20 meters. About. Okay, as a really quick estimate sort of thing. So this is a couple important ideas, and that is when you get to a peak, when you change directions, your velocity is 0. That's always going to be the case. You can't change directions from positive to negative or negative to positive without passing through 0. That is something to know. When you change directions, your speed is 0. Okay? So that's kind of something important to get out of this, I think. All right.